Welcome everybody. This is yet another instance of State of the Shell. As Jonathan Blandford once said, this is an acquired taste kind of presentation. Hopefully this one is going to taste very good. So yeah, let's get started because we have a lot to talk about. And Carlos, please.
Yeah.
Your turn.
Yeah, so I'm going to talk about input, and yeah, this next slide. Yeah, so in 336, we introduced ClutterSeed, which is the actual first step towards a number of input refactors. So in previous versions, we moved a lot of backend code from Clutter, so it lives together with the rest of the backend code in Mutter, which means that actually is, for the most part, backend independent, and the backends, they actually deal with all the backends, which is good to have all the backend code together. So yeah, ClutterSeed is actually the actual first refactor that you were allowed to do with this. And yeah, well, it's not that much exciting on itself, but it's more about what it's going to get built on top, basically. So yeah, well, ClutterSeed is an owner of input devices, and it's a source of events, basically. So well, it has other minor roles, but we can move forward. Yeah, so next slide, please. Yeah, so there's been some work on the input thread, and yeah, well, these diagrams are actually fairly nice. The arrows, they look pretty definite in the direction they go and whatnot, but actually most of the work has been in untangling all of, well, quite some bits in upper code that was spoken in different ways into the backend code. The final goal of this is to make the input thread, the blue circle that you see there, to be actually, well, to be able to figure out from one pointer position and a number of events what would be the next pointer position without external agents, basically. So the easy part is sending events to the UI, which would live in another thread. And yeah, well, this is just a queue of events. It's nothing really complex on itself. So next slide. Yeah, this is more of the where the main refactors have been done. It looks, as I say, yeah, it looks a single arrow, but there's quite a number of interactions between the UI thread and the input bits, which would be virtual devices, warping pointers. Warping pointer is when that pointer moves from one place to another in the screen. But there's also a number of others, like device querying or modifier querying or pointer barriers or pointer constraints or pointer locking, or yeah, there's quite a few of these. So this has been mostly streamlined, so the interactions are easier between both threads. And yeah, well, it will hopefully pay out. So next slide. This is where we involve KMS and whatnot. KMS could be the lower level parts doing the cursor plane position changes and whatnot. So yeah, in this case, well, actually the arrow would be in the other way around, because it relies on the same mechanisms that device queries in the UI thread. So the final result is that the KMS bits are aware of the final cursor position at that point of rendering, and they can use it and upload the new state to the cursor plane. And next slide, please. And then there's the actual painting of the cursor. There's the UI thread is going to take care of this. It, of course, needs to pick on a position and figure out which cursor makes sense based on that position, and then do the updates. Eventually, it would be nice to make the cursor be an opaque object that can be pushed to the game speeds, holding all the animation details like the clock, the spinner, and whatnot. So it's all happens in the KMS without involving the UI thread. At the moment, all updates, for example, to the next frame in the cursor animation could be happening in the UI thread so far. But yeah, well, subject to change. Next slide, please. And the potential benefits, they range from immediate to pie in the sky, but yeah, well, there's some things that are getting closer thanks to this. So yeah, well, the most immediate benefit is that we don't miss any live input events. Should it happen that the shell would be blocked, the UI thread would be blocked, say some extension doing something crazy, we will still get to process events and put them in our own internal queues. So live input wouldn't complain loudly as it does currently if that happens. The next one would be no blocked pointer cursor. No. Sorry. Previous one, please. Yeah. So no block pointer cursor. It would mean that the UI thread is not actually involved in updating the cursor plane position. So it could happen independently of the UI thread being blocked or not. It should result in more reactive pointer motion and whatnot. It also helps in better handling of high frequency devices like the 1000 Hz mice and whatnot. So we currently are doing motion compression pretty deep in the stack, and this design actually pushes or makes it more mandatory to put this event compression higher up in the stack, which actually means that we could, for example, handle or deliver Wayland events at full rate but only handling or compressing motion events before handling them to the clutter bits. So the shell would update at 60 frames per second or 75 frames per second, and you would still get the full motion, the full stream of motion events to the clients. And the next thing would be that it would allow better use of the cursor plane, as in moving it across devices and whatnot. Right now, well, the software plane is a last resort, so it would be nice to move them between devices. For example, if you paint with a tablet, you could get a pointer cursor which is currently rendered with software. So this helps. Yeah, next slide, please. Yeah, and last but not least, we have the touch mode, which, it's basically a low-level toggle, which will allow the different bits in the UI to adapt to this change. It, for example, there's a patch that should be merged at some point to allow the rotation lock to just disappear if you put the keyboard on a 2-in-1 device and whatnot. So it behaves like a tablet when it's like a tablet, and it behaves like a laptop when it's like a laptop. So yeah, well, the exciting things happen on top of that. And yeah, this is my bit.
So this will be about the changes we have done to the frame clock that drives the rendering of the shell. Next slide, please. So first, a bit of a history of how it looked before. Clutter, as you all know, started out as an application toolkit. Every application would create one or more stages, which more or less is the same as a window. And we would have a single frame clock that drove the animation of all these windows in a kind of monotonic way. It worked fine enough for this for years, even when we started to use Clutter as a compositing manager for the X11 golden days. It worked almost just as well, because with the X11 window manager way of using Clutter, we would still paint to a single window, and we would just care about driving that window. Not too much different from a regular X11 application. Next slide, please. Then things becomes more complicated as we enter the Wayland era with a native backend that talks directly to the kernel mode setting instead of having the X server do that for us. It works quite differently from an application because we have more responsibilities in dealing with the hardware beneath. After having forked both Cobol and Clutter into our own Mutter version, we started to split the rendering passes up into different pieces. Initially, we did this by rendering certain areas of the stage separately, and we call those areas views. It's more or less, if you have multiple monitors, we would render the area they occupy individually. We got, for example, monitor rotation using OpenGL by doing this, and fractional scaling by doing this. Eventually, we took it to the next step, and instead of just splitting the region up, we actually did it per monitor, or actually per CRTC, which is it's a component in the graphics card that drives the monitor. Next slide. Until quite recently, we still used the good old frame clock from the application days of Clutter, but it didn't really fit the way where we want to implement the display server that has to talk to different monitors that render at different clocks. So how it works is more or less a monitor is driven by a CRTC that has its own clock. Usually the clock ticks at a certain refresh rate, more or less, what you configure in the settings. It will run at that interval, unless you have a virtual refresh rate monitor, but ignore that for now. These different monitors, they render at different, or they update it at different times, even though they have the same clock frequency, or they have different clock frequencies. They're 144 hertz and 60 hertz and 75 hertz, and they simply have they render at their own pace. Next slide. So here's an attempt at an illustration. See that there's supposed to be red lines saying where we render. Let's see. They seem to have disappeared on the converting to PDF, but I will try to explain where they're supposed to be. At the beginning of each blue arrow, there is a frame that is drawn, and the end of the blue arrow is when the frame is presented, or the monitor is updated. And the first two blue arrows we would render at the, let's say the first monitor has a 75 hertz update rate, and the lower one has a, let's say, 45 or something. We would render at the upper monitor rate for a couple of frames or 3 frames. And then something would change on the other monitor, the slower one. And more or less the result that we would end up with is that both monitors will render at the slower monitor's rate, because we have to wait for the second monitor to finish before we can render the next one. Which, if you had a fast and a slow monitor, the fast monitor would render at the speed of the slow monitor if the slow monitor had any updates. And that's kind of annoying if you have a fancy monitor that you can't really make use of. So next slide. So the single frame clock that try to juggle all these kind of scenarios, of course, more or less standing our way for making any significant progress in this area. As you could see in the previous slide, they were waiting for each other to paint when they both painted, and it was kind of complicated to try to juggle different monitors with different capabilities and requirements, and so it was decided at one point to just split it up to multiple ones. Let's take the next slide. So we created a completely new frame clock, call it the ClutterFrameClock. Already we had split up the rendering or the painting of the stage, the screen, of all the screen content into different dedicated views. Each view would correspond to a monitor. So we already had that in place. So we put one of these frame clocks in the view, and then have one frame clock drive a single view. It's pretty much how it works. It makes the clock much simpler because it doesn't need to handle as many things at the same time. Next slide. Here you can try to put in your head again how it's supposed to look when the red squares are there. The fast monitor now doesn't care at all about the slow monitor, it just draws at its own pace. And the slow monitor starts to render its triangle cone thingy, and it doesn't. It does it also in its own pace. So next slide. That's not enough, because Mutter is not only a toolkit for compositing windows and painting onto monitors, it's also a compositor user interface toolkit used by GNOME Shell to implement all the fancy animations and widgets and Chrome and everything. It has an animation framework. In the past, we used something called Tweener, but since a few versions ago, we use Clutter's own pretty capable animation framework. But there's was one culprit with this, and that is that the framework assumed that there was only a single frame clock that drives everything, and it would just automatically attach to it, and all would be well. It would just get it animation frames, and it would just animate on. Next frame. The next slide. So we would have to make a connection. Each of the animation would be driven or so by an object, a Clutter object, called a timeline or a transition. We already have these objects, so if we tie one of these objects to an actor is a widget on the stage, for example, a window or a button or a menu or something like that. We would tie an animation to an actor. An actor would already know on what views it would be painted on or was painting on. And now with a new frame clock thingy, each view had a clock, and voila, we could find a suitable clock by just looking at the actor the animation was tied to. And by that, we would just, yeah, next slide. Yeah, by that we would have animation objects that would just automatically animate at the speed that they were actually on, assuming you made the right connection to the right actor. And that required API changes in Clutter or Mutter. But GNOME Shell pretty much completely wraps all the animations into a few helper functions or a helper object. These so-called ease functions take actor properties and put a initial value and a final value, and then they will create a transition of a smooth movement between the two. And an adjustment is similar to that. We will just fix these two kinds of animation methods to automatically find the right actor, and then it just kind of worked. If I remember correctly, there was just 2 lines of JavaScript code that was needed after fixing those two in all of GNOME Shell. So for extension developers, that hopefully wouldn't need too much changes, assuming you use the Clutter animation framework. So here's a screenshot that was kind of hard to read, but on the left one, I think it's a 75 Hertz monitor that I run GLX gears. And the right one, I run Western Simple EGL on a 60 Hertz monitor, and they run at their supposed to run speed. And that's the 60 Hertz, yeah. And that's the whole goal of the split up. Yeah, next slide. And that I think that's it for me. Thank you.
Yep. Next slide is the layout machinery. And this is about Clutter's layout machinery. So that machinery got quite a few improvements last year, over the cycle. And the most important improvement probably was the introduction of the shallow relayout mechanism, which was done by Daniel. So thanks to him. The way this works is, like, the basic way layout works is that it goes from top to bottom usually. Like, you start allocating actors at the topmost actor, which is usually the stage, and then you go recursively down to the actor which actually queued the relayout. So you basically always have to allocate the actors up the chain to allocate an actor down the chain, and that's quite expensive. And the way what we found was that there is a way to improve this thing, because there is the no layout flag, and the no layout flag is a flag which tells Clutter that your actor does not need to be allocated by the layout machinery. So Clutter can now make the assumption that this actor has to be allocated by using static positioning, and Clutter can take a shortcut, can basically allocate the actor directly instead of starting at the stage and instead of going down the whole hierarchy. And this has made this has been quite an improvement for performance, because it has made allocating actors like windows significantly faster, because we no longer have to start at the stage with allocating. Then we've been landing various bug fixes in Clutter. Those mostly have landed because we've found bugs when implementing new layout managers in the shell. So yeah, those were quite a few bugs, and they're mostly fixed now, I guess. Then we have removed Clutter allocation flags. That was a change. So Clutter allocation flags basically were used by Clutter during the allocation cycle to pass on information to children which were allocated about the allocation cycle. And there were 2 of those flags. They were both pretty much unused, and one of those flags was called absolute origin changed. Now this flag was used for notifying children that an actor's origin changed. So you'd have a position of an actor, And if this actor moves, you would use this flag to notify all the children of the actor that the actor has moved. So the problem with this flag is that to notify those children, you would have to, so because it's a flag which gets passed to the allocate function, to notify those children, you would have to reallocate all those children. And now if some children don't have to be allocated, you would have to allocate them because the flag has to be passed to the child. So that was quite expensive too, and we can now completely avoid it because we got rid of this flag. So the next point, that was quite a big change in the layout machinery, was the enforcing of invariants. So basically, Clutter defines a few invariants for actors which are managed and set by Clutter itself. And one of those invariants is the mapped state. Now, the mapped state basically saying whether an actor is getting painted or not. And the way this works is as soon as the actor is on a stage and its parents are visible and the actor itself is visible, the actor is mapped. And there's a trick, like if the actor is not mapped, if the actor is unmapped, we can obviously know that it's not going to be painted. So we can skip allocating this actor, for example, or do other optimizations. And we're now doing a better job enforcing those invariants. So that basically means that we found a few bugs through this change, and yeah, it should make debugging a bit easier because it should be better to find issues with that thing now. So let's go on with the next topic,
which is the DMA-Buf Screencast. I guess that's my turn. Hopefully everyone can still hear me. I'm sure you're going to tell me if you're not. I'm going to try to be real quick here, being mindful of time. So essentially, the DMA-Buf Screencast is a way to avoid copying pictures over different memories. In this case, we're talking about the GPU memory and the regular RAM memory. So essentially, when you're screencasting, what usually happens, and this is a very small slide deck here, but I guess you can all see. So suppose this is your monitor. You're seeing GNOME Shell here, beautiful as it always is. And and then you want to screencast your monitors, right? So you want to record something. So when you start recording, then Mutter starts copying what's available on your screen to RAM memory, which is over here, and that's extremely expensive. After that, Mutter hands the application who's recording this, the frame that you just copied over. The application does whatever it wants with the frame, and then it's destroyed. That's usually how it works. With DMA-Buf, we got a different cycle here. So instead of moving the frame down to RAM memory, we create a copy on the GPU side of things using the lit operation, which is extremely fast compared to downloading it to RAM. We have to create a copy because we don't want to lock your monitor frame until the application is using it. So we create a copy, we copy it over a different buffer, and we give the application a file descriptor, essentially a number, an ID for where this is in GPU. The application can do whatever it wants with this file descriptor. It can even download it to RAM memory, but at this point we don't care because Mutter is already not doing that, which means you can still have a smooth screencast experience with Mutter. And then we have a recycling mechanism. So instead of destroying it right after the application tells it's done using it, we can reuse this and copy over the next frame or 16 frames after that, and keep reusing stuff until the stream is done and we can destroy everything. So this is the DMA-Buf Screencast. It's a much pleasant experience when screencasting. Next topic is paint nodes. So paint nodes are basically what use the core of what was going to be Clutter 2.0. And it's composed basically of a two-step rendering process. So first we go through all the UI elements around and ask them and collect the paint nodes. which are basically operations on how you want to draw. And then after the collecting phase, you go to the painting phase, where we go through each node and ask them to do what they want to do. So this is a pretty small self-contained example here of a paint node tree. So we start with a root node, and then we want to paint some color here, and then we want to paint something, but this other something is clipped. So we paint inside a very limited region. We paint a texture here. Then after that, we want a color painted on a layer node, basically a GIMP-like layer where you can combine them later or not. This is a very small example of how paint nodes work. And this is what we are going in the direction of. This will allow us to add some cool stuff, cool features on top of the rendering process. So at this point, right now, Clutter effect is fully ported. Off-screen effects are ported. The GNOME Shell blur effect is also ported to use paint nodes, which was, it required some more API on the paint node side because we couldn't express all the operations that were required to paint a blurred version of something using only paint nodes. So we had to add more API, and voila, it works. Next step is adding a way to profile regions of paint nodes, paint node subtrees. So for example, if I want to know how long does it take for me to draw this subtree here, I'll be able to create a new node, a profiler node, that will check how long it takes to draw that. And then after that, we can port GNOME Shell entirely and hopefully make all of the rendering completely shader and GPU based. And yeah, so switching gears a bit, so let's talk about GNOME Shell now. Probably most or all of you are already using it, but we have a new lock screen. I can't live demo it, but there you go. It's a very, it's a more beautiful experience in my personal opinion. It's long in a queue to be done, and it has landed in GNOME 3.36, and there you go. This is part of what happened during the past cycles. And what's queued for GNOME 3.38 is a customizable app grid. I'm not sure if it's a very good idea for me to try and screencast this right now, to share it. I mean, I could do that because it would prove that DMA-Buf screencasting is fantastic, but I'm afraid of doing that and crashing everything. But anyway, so here you can see that I'm on the second page of the icon grid. It's completely out of order. It's in the precise order that I want to. And okay, I'm being I've been asked to live dangerously. So let's do this. Hopefully you can see my screen. I'm sure you let me know if you can't. There you go. I can see my screen. That's a good sign. So there you go. We have a customizable app grid here. As you can see, this is my personal grid. I've adjusted with the applications that I use the most. I can drag something here. For example, GNOME boxes in this position. It's probably not as smooth as I'm seeing because I'm screencasting, but anyway, I can do like this, or for example, get this folder, drop it here. There you go. So yeah, this is the customizable app grid for you. Back to the slide deck. I'm handing it to Jonas to talk about the Dialog Redesign.
Yep. So something else that we landed in GNOME 3.36 last cycle was the redesign of dialogues. And we basically did that because there was an open issue on GitLab about redoing them for quite some time by the designers. And they rightfully complained that the dialogues were quite inconsistent. The design was different over different dialogues, and yeah, some of them also looked outdated. So they've been wanting to redesign them for quite some time, and so they did mockups for every single dialogue. So thanks to them, that was quite a lot of work because it turned out that there are a lot more dialogues than you'd think in GNOME Shell. And yeah, we've been able to land it in GNOME 3.36, so most of you should already have seen it. In case you haven't, we have a few screenshots in the next slides. Gorgeous. Thanks. Yeah, right. So on the left, there are the old ones, and on the right, the new ones. And we have even one more slide. If it loads, yeah. So in my opinion, that looks way better, but yeah. Next up are the changes to workspaces in the overview. So in the overview, we basically we have this those windows which are shown in the overview, and we have like overlays on top of those windows which show the title and the close button for those windows. And previously, we've implemented those labels completely separate from the windows. So they were positioned statically in a separate class, and we've basically had to track the window movement, the movement of the windows, and everything the windows did, and replicate that thing for the overlays, so they stay in sync and stay positioned correctly. Now that thing led to quite a few interesting bugs. I guess most of you have already seen the bug with the titles of windows being either too small or too wide in size, and the label doesn't really fit or something. So that is hopefully fixed now. Yeah, we've also moved the code of the overlays into the class of the windows itself. So that should hopefully be a nice cleanup. And we've also switched to positioning those overlays using Clutter constraints now. So that is like the new way you're supposed to do things in Clutter, which has been around for some time, but we're actually using it now for quite a few things. And it's quite neat because we can basically tell Clutter to bind the size and the position of the overlay to the actual window, and Clutter is going to do the rest for us. So we basically no longer have to care about those things. Next slide, please. Yeah, so this is about the layouting of the windows in the overview. And it basically was the same thing for the windows as it was for the overlays. We've also positioned those statically. So we had set like a fixed X and Y position and a fixed width for the windows. And the old code was like quite complicated. It was quite intertwined with different classes and stuff. And yeah, so it was not great. And we've now changed this completely to be positioned using a custom Clutter layout manager. So Clutter layout manager are as Clutter constraints the way to do things if you want Clutter to take care of you for the layout. And yeah, this led in the end to a way separated code where we can theoretically reuse parts of it elsewhere. So if we need to, yeah, that's it, I guess. Next.
Okay, so this one is on me. Next slide directly. So we got better extension support in 3.36. What we see here is a newish extensions application. It's actually based on a helper tool that has been in GNOME Shell forever. But it has been split out into a backend part that shows the actual, that interacts with the extension code, and a redesigned front end that has been split off from GNOME Shell itself and can be split separately. And it's of course available on FlatHub as well. You see the orange markers, those mark extensions that have updates available, because after 10 years, we are finally supporting updates. Yay. So next. This is what I commented on the previous image. There's also now a CLI tool to manage and interact with extensions. It's mostly targeting developers, but if you're using the old GNOME Shell extensions tool, command line tool, the new one has bash completion, so it's a huge difference in practice. Next, please. There have been some improvements to the calendar dropdown, and there are more to come. So what we see here is there were some refinements in the weather sections. Events have been split off from notifications and moved, well, to the calendar, which is kind of obvious. And we now have do not disturb functionality that was always there, but it has now like a proper control inside GNOME Shell itself. Next, please. And there have always also been like the backend used by GNOME Shell to interact with Evolution Data Server has been largely rewritten and should be like a lot faster now. And we have like an ongoing Summer of Code project, which will hopefully give us like new and better notification presentation. Go to the lightning talk on Monday. Next, please. And of course, there have been like a lot of smaller changes over the last year. Some of the notable ones are that we have like better support for system user sessions, which basically mean that every process that is launched by GNOME Shell is placed into a separate scope, which will allow for some like resource control in the future. There has been like a talk specifically about this topic by Benjamin Berg 2 days ago. Go watch it. The next one is parental control support, which is like a new panel that is being added to GNOME Control Center. And if applications are restricted, they no longer show in GNOME Shell if parental controls are enabled. Again, there has been a talk about this earlier by Philip Withnull, and the recording should be out or should be out soon. And another like minor improvement is that the GNOME Shell service that provides color picking now previews the color under the cursor. So if you look at these, who controls the red dot? Oh, yeah. So the dot under the cursor there does actually show the color that is underneath the cursor, and that will be picked when you confirm the selection, which is like a cute little UI hack. Okay, next.
I guess this is all that we have. Are we on time?
Yeah, you are really on time.
1 minute left, I think. One minute left.
You can start your guitar playing.
So I heard that there's gonna be a social event. We can play there.
So you can switch, to the other pad for the questions. There is already a lot of them, and please,
I'm
please
actually answering the first question, which is, would you like to play some music at the end?
Okay, sorry. Please go on.
So the next question here, probably for Jonas Ådahl, is: do all KMS drivers support separate scan out of the cursor?
Most do. In practice, all the ones that we actually use support a kind of like a cursor plane. Some drivers support not a plane, but a way to set the hardware cursor. But most do.
Okay. Our next question is probably for me. The DMA Screencast. Doesn't the app need to download to RAM anyway? The app doesn't necessarily need to download the contents of the buffer. It can import the buffer using EGL and not move it away from the GPU side. But one of the cool things about sharing the DMA-Buf is that even if the app downloads the buffer from the GPU, it doesn't really affect Mutter like it used to. So the app's going to be slow, probably it's going to skip some frames, but Mutter itself, it's going to stay untouched. Hope that answers the question. So next question is, can somebody elaborate on why bleeping is required on the GPU memory? Can't we just reuse? I said something about we can't unlock. The point is, we don't know. When you're screencasting, we can't just let the app have access to what we could, but actually it's not a great idea, because have access to the monitor contents, because the monitor contents can switch if you're drawing something different, if you move your cursor, or if the app updates. Anything can happen that makes the monitor change the contents, and we don't want the application who's reading get the monitor right in the middle of that, right? And most importantly, we don't want Mutter to have to wait for the application to finish until it can switch to the next frame. So we create a copy of the buffer, and then Mutter can continue rendering while the application has a fresh copy there for you to use. It can take as much time as it wants. It can do whatever it wants. It can download, can import, whatever. And Mutter can still continue doing its own thing in parallel. So that's a big reason. Okay, the next question is not really a question, but a huge thanks for the blog entries on the Shell development blog work going on. It's been really helpful, and I've learned a lot from it. So that's great feedback to hear. Thanks for whoever said this. Yeah, we're happy to do that. If you don't know what we're talking about, so we have a blog. It's blogs.gnome.org/shelldev. Fresh news directly from those who make the changes. The idea here is that you can have a reliable source of information when it comes to GNOME Shell and Mutter, without over-exaggeration or selling the changes that we're doing. So yeah, do read it, share it, follow the blog, share it on social medias. We are trying to stick to a monthly development schedule of the development reports with a success rate of about 80%, which is pretty good. So yeah, thanks for this feedback. Does anyone want to say something? Can I proceed? The questions? Okay, I'm going to take it as proceed, please. What's the plan for supporting restart of a Wayland session without losing running apps?
I can take that. So there's one idea that is being explored, actually currently being prototyped by KDE, which is kind of like a Windows session management Wayland protocol, which means that, for example, GTK or Qt would ask if it sees that the display server is restarted or crashed or whatever, it would try to reconnect and ask itself to have its previous state restored, and GNOME Shell would have to store some kind of state in some place outside of its own process memory that it can look up again to restore any application that wants to restore itself. That's the one approach that is currently being explored for this.
Thanks. So we got a bit more questions. Do we have time for them? I guess nobody's complaining, so I guess we have time for them. Any plans for improving extensions updates story? Because that's for Florian.
Yes, but I'm not sure I understand the question. If it means never making any changes that could break an extension, because that's impossible to happen, because extensions simply have access to all the GNOME Shell JavaScript code. or if it refers to like the newly added updates, where GNOME Shell like checks like every day the installed extensions, whether there are updates available, and downloads them. I mean, if there are like particular improvements people are interested in, please file issues on GitLab. But so far it works as it's intended to work.
I'd just like to mention that there's going to be an extension reboot talk by Sri. I think it's tomorrow, right? So make sure, if you're interested in this topic, watch it.
I think that's all the time we have for the questions. Please, you can easily respond and ask questions to the team in the chat. Thank you very much for this presentation on the shell. We will be back in about 8 minutes. No, at 17:45 now. Thank you.
Thanks, everyone. Enjoy.